Last time we ran a batch through W with a single matmul, but we never asked the real question: what does multiplying by W actually do to the points in space? Think of the plane as a stretchy sheet of graph paper. A matrix grabs that sheet and warps it. It can spin it, stretch it, or skew it sideways. Crucially, grid lines stay straight and evenly spaced, and the center never moves. That's what linear means. Watch the two basis arrows, the unit step right and the unit step up. Wherever those two arrows land after the warp, that completely determines the transform. In fact, the columns of the matrix are exactly where those arrows go. Apply one transform then another, and the combined effect is the product of their matrices, B times A. And the determinant of a matrix is the area of the little square the basis arrows span after the warp. Bigger than 1 means stretch, less than 1 means squish, negative means a flip. Here's the punchline for deep learning. Stack two linear layers with nothing between them, and you've just multiplied two matrices, which is still one matrix, one transform. No matter how many you stack, it collapses. That collapse is exactly why we wedge a nonlinearity between layers. Here's the whole thing in one file. We take a rotation and a scale, apply them to the unit square, compose them, and confirm the composed determinant is the product of the parts. We see nothing random here. We define a 45-degree rotation matrix R and a non-uniform scale matrix S. We build the unit squares corners and the two basis arrows as columns. We apply S then R as one composed matrix, M equals R at S, transforming every corner. We compute det R, det S, det M, and check det M equals det R times det S. We print the determinants and plot the original square against the transformed one. Multiplying matrices warps and stacks space, but it can never bend a line. Next time we measure inside that space, norms, dot products, and projections.